All right, good afternoon. So we will continue with paging now. So we are covering chapter 8 of the book. And we have talked about the paging. And we have talked about how we can divide the virtual address space and the physical address space into pages. And this requires a mapping to be done between the pages and the page frames of the physical memory. Okay, if you remember that. So this is a different memory management technique. Before that, we have seen the technique that is contiguous allocation, where assuming each process is required to be put into memory entirely, okay? So we were trying to find space in memory that is large enough to hold the new program, okay? Assuming the programs are brought into memory as a whole, then whenever a new program has to be loaded into memory, what you were doing, you were just looking to the memory, allocated and unallocated space, and you were searching for an unallocated space, free space, into which we could actually put the new program. This was the contiguous allocation. But the problem with that was external fragmentation and so on, right? So a program also has to sit in a contiguous space in physical memory. That is the requirement with contiguous allocation. So how can we relax that? So a memory management technique, for example, that does not require a program to occupy a contiguous space in the physical memory. That would be more flexible, right? So that, for example, some portion of the program will be sitting in some location in memory, some other portion will be sitting in some other location, and so on. This is more flexible. And paging allows that, because now you divide the program into pages, and you put those pages in physical memory in empty frames. And those empty frames do not have to be contiguous, right? So paging is a very flexible memory allocation scheme where the physical memory allocated to a process does not have to be contiguous. And we achieve that by dividing or by considering the physical memory divided into fixed size blocks called page frames, okay? And similarly, the logical address space is considered to be divided into fixed size blocks called pages, all right? So, but this requires mapping to be done. For example, a logical address has to map to a physical address. The CPU operates with logical addresses. It generates a logical address. Then the hardware has to map that to a physical address and has to go there in physical memory to retrieve the corresponding value. And that mapping is done by the hardware by use of the page table, okay? So page table tells where each page of the program is loaded in memory, in which frame, right? It has this mapping maintained in the page table. So the operating system actually sets up the page table, but the hardware uses that page table to make the translation, right? So whenever the CPU is executing the instructions, for every instruction we make at least one memory reference. And for each reference we convert the logical address to a physical address. These memory references that are done by the CPU are logical memory references. So we convert those addresses to physical addresses on the fly at runtime, right? So it has to be fast, therefore it is done by the hardware. The hardware looks to the page table, finds the page frame number, and so on, concatenates that with the offset, obtains the physical address, fetches the value from there, and so on, okay? But the setting up the page table is done by the operating system. When, for example, the program is loaded into memory, the operating system knows into which frames the pages of the program are loaded. Using that information, it generates the page table, right? It tells, okay, this page number is loaded into that page frame number, and so on, okay? So page table setup is done by the OS and is used by the hardware while translating the addresses to physical addresses. So let's look to this address mapping, how we can translate the logical addresses to a physical addresses. So let's start with a simple example here, okay? So assume we have a very small logical memory that the program is using, 8 bytes of logical memory, okay? Assume these are the characters stored in the logical memory. Of course, it doesn't correspond to a program, but assume this is the content that is stored in the logical memory that we would like to map. Okay, so the logical memory is just 8 bytes, and these are the addresses. So for 8 bytes, how many addresses you need? 8 addresses. How many bits you need to have 8 addresses? 3 bits, right? So basically here we have 3-bit addresses. Logical addresses are 3 bits, okay? M is 3, the number of bits in a logical address. So we can generate at most 8 logical addresses, and this is enough to address all the bytes of the logical memory, right? So now this is the logical memory. Assume the program is occupying that, and the program content is represented by these characters assume. So now assume this program, this logical memory has to be loaded into memory, physical memory, okay? So assume these two frames were empty at that time so that these pages are loaded here. So this green page is loaded to here and that blue page is loaded to that frame of the physical memory, okay? So we have this as the physical memory. Assume we have a physical memory that is 16 bytes, okay? That can happen, right? Actually, this is not very practical, but assume we just have a physical memory that is 16 bytes. And now these are the addresses of those bytes, okay? So for 16 bytes, how many addresses do we need? 16 addresses if each byte is addressable. Then for 16 addresses, we need how many bits? 4 bits, right? So each address here, physical address is 4 bits. So now let's consider now the mapping. This page is loaded, assume, to here. So the content now of that frame is this, okay, that page. So a page corresponds to a content. Here a frame is a container, right? So that frame is actually containing now that page, okay? So the content of that page is ABCD. And that frame, for example, frame 10 contains that page whose content is A, E, F, G, H, okay? So assume this page is loaded here and that page is loaded. So what is the mapping now? While the OS is loading those pages into memory, physical memory, it has to generate the page table, set up it, so that the page 0 is loaded to where? Into which frame, page 0? 11 or 3? It is 1, 1, right? So basically it is 3, page 3, frame 3, frame 0, 1, 2, 3, right? And page 1 is loaded into which frame? Into frame 2, right? So this page table is set up by the operating system. Now assume now we are making memory references. We are wondering, we would like to access those bytes. So the CPU generates, for example, logical addresses to retrieve the values, okay? If, for example, it generates such a logical address, 0, 1, 0, we are wondering what the corresponding physical address will be. And now we will describe the mechanics to obtain that. So before that, however, let's make some observations. Here, the physical address space is divided into pages. So what is the page size here in this simple example? How many bytes? Page size? 4 bytes, right? So, and here 4 bytes are stored in a page. So if you would like to actually assign a local address to every byte here, an offset or a displacement from the start of the page, how many bits do you need? 2, right? So basically 0, 0 will be the offset of that, 0, 1 will be offset of this, 1, 0 will be the offset of that character, and 1, 1 will be the offset of that character, okay? So in those logical addresses, basically, this most significant bit indicates what? Page number, and these two significant bits indicate offset inside that page, okay? So then, for example, consider here, we have the frames, and the frame size is equal to the page size, right? So the frame size is 4, 2, and the offset values of the bytes stored in a frame. For that offset, how many bits do we need? 2, again 2, right? So, and for the frame number, how many bytes do we need? How many frames do we have? 4 frames we need, right? How do we obtain that number? We divide the physical memory size into the page size, and we obtain the number of frames that are in the physical memory, right? So this is, for example, frame 0, 0, 0, 1, and so on. So, for example, consider a logical address here, like that, 0, 1, 1, 0, okay? Which bits indicate the frame number? And which bits indicate the offset in that frame? Most significant 2 bits indicate what? Frame number, and the least significant 2 bits indicate the remaining bits indicate the offset, and so on, right? So, for example, all the addresses in that frame start with 1, 1. And the remaining 2 bits are used to offset the bytes, okay, individual bytes in that frame. So consider, for example, that page loaded to here. The offset of C is what? 1, 0, right? Do you think that the offset of that is changing in the frame? No, right? It is the same. The offset of C, character C, in that frame is 1, 0 again, okay? What is changing is what? The prefix of the address, right? Here the prefix of the address is 1, 1. Here the prefix of the address is what? 0, right? So 0 has to be mapped to 1, 1, right? As in the case here. So basically then, the mechanics to do the address translation is this. Whenever you have a logical address, let's say 1, 0, 1, okay? So it is the address of character F. And now you would like to access that character, okay? So F is stored somewhere in the physical memory. So you know the address of that in logical memory, which is 101. So you want to find the corresponding physical address. So if you look to here, you can easily find it. But how does the computer obtain the physical address? So that logical address is divided into two parts. Page number part and offset part, right? What is the page number part? Offset part? So 01 will be the offset part also in the physical address, right? So it will remain the same. But now page number 1 is loaded into which location in the physical memory? How do we know that? Page table. We go to the page table and find out the corresponding frame number, which is 10, right? So now we have to concatenate that 10 with what? With the offset of F. So then the resulting physical address will be what? 1001, right? So let's do a check whether F will have that address. Yes, F has the address 1001, okay? So this is the way that we obtain the physical addresses corresponding to logical addresses. So this example shows that, a simple example. So from that we can generalize the algorithm that is executed by the hardware to find the corresponding physical address. So assume the CPU generates a logical address, okay? That logical address is divided in two parts, page number part and page offset part. So this is the logical address. It is divided in two parts, and page number part and page offset part. So some number of bits are used as the page number. Some bits are used as the page offset, okay? How many bits do you need to use as the page offset? To what it depends? Page size, right? If the page size is X, what is the number of bits required? Log 2x, right? Log base 2x, right? So for example, if the page size is 4096 bytes, 4 kilobyte, what should be the number of offsets, bits in the offset to indicate the offset? 12, right? So in this way, you can, for example, compute the number of bits required to allocate as the offset and so on. So the remaining bits will be what? Will be indicating the page number, right? So basically, if the logical addresses are m bits, and if you allocate n bits to indicate offset, then m minus n bits will be indicating the page number. Is it clear? So basically, you divide this logical address in this manner. You obtain the page number. You consider some number of bits, m minus n bits, as the page number, and the remaining bits, n bits, will be considered as page offset. So now, what you will do, you obtain those values, page number and page offset, from the logical address. You use the page number what? You use that as an index to the page table, right? So that you go to that location in the page table and obtain the corresponding frame number, right? So you use that page number, P, as an index to the page table. You go to that entry in the page table and retrieve the frame number corresponding to P, which tells on which physical frame P is located, right? And then you obtain the frame number F, and you concatenate that with the value D. You obtain now the physical address, okay? This is the algorithm that is used. So let's do an example here. So this algorithm is shown here. So all this is done by the hardware, because you have to do this with every memory reference. It has to be fast, okay? And for a program that's executing, you at least do one memory reference for every instruction that is executed, okay? So now assume CPU generates a logical address. It is divided into two parts, or it is considered to be divided into two parts, page number part and offset part, P and D. D is displacement offset. So you use P as an index to the page table. That means you go to the P entry in the page table. You look to the entry P, okay? You find there the frame number corresponding to that page, which tells that that page is loaded actually into that frame, is sitting in that frame inside the physical memory. So then you take that frame number and concatenate that with the displacement, and you obtain the physical address. You give this physical address to the memory bus, so that the memory chip takes that physical address and gives you the value sitting at that address. Okay? Is it clear? And this is done by the hardware, as I said earlier. So basically, assume we have a program that is sitting on the disk at the moment, okay? So it is considered to be divided into pages, right? Assume that program has 4 pages, sorry, page 0 through page 3, okay? So when that program starts up, what happens? That program is loaded into memory. OS loads that and finds out some number of free frames into which those pages can be loaded. How many free frames needed for that program? 4 frames, right? So assume the operating system just finds out those 3 frames and now loads those pages into those 3 frames. So page 1 is loaded into frame 13, page 0 is loaded in frame 14 and so on. So operating system loads those pages of the program into those 3 frames of physical memory. In this way, the program is loaded into memory, okay? So as you see, the program is now no longer occupying contiguous space in memory, right? It is occupying page frames that are scattered around in the physical memory. So now the operating system, while loading those pages, it also sets up the page table. It, for example, at entry 0, it writes the value 14, indicating that page 0 is on frame 14. In entry 1 of the page table, it writes the value 13, indicating that page 1 of the program is loaded actually in frame 13 and so on. So this page table is set up by the operating system as well. Of course, while allocating the frames to the pages, then the operating system actually manages the free frame list. Initially, the free frame list is this. These are the free frames that are known by the operating system, which frames of the physical memory are free at the moment. Okay, it maintains a list of free frames. So whenever it allocates a frame, it removes that frame from that list. It is no longer free, right? So when that program is loaded into memory, the free frame list will become something like that. Only frame 15 is free, so that list will contain only that frame. Okay, is it clear? So how can we implement the page table? So where do you think the page table is sitting? So page table is a sequence of entries, right? It can be just a sequential array, one-dimensional array. So where do you think it will be sitting? How many entries do you think you will have in a page table? Large number of entries or small number of entries? Large, right? Depending on the address space, actually, logical address space. If you have too many pages in the logical address space, then you will have a large page table and so on. So usually it is very hard to fit a page table into small amount of registers in the CPU. So therefore you usually do not have the page table in CPU. So where do we have the page table? In the hard disk maybe? No, right? So in the main memory. So page table has to be in main memory. So, and another question is this. Do you need a separate page table for every process or just a single page table used for all processes? Separate, right? Because each process has a logical address space, some number of pages that has to be mapped, and those pages has numbers starting from 0, page 0, page 1, and several processes may have the same page 0. And the page 0 of one process may be sitting in some frame, page 0 of another process may be sitting in another frame. So we need several mappings, right? So therefore each process has its own page table, okay? So page table is kept in main memory. Then when a process is executing in CPU, its page table is used while doing the translation by the hardware, okay? The hardware uses its page table. And when a context switch happens, then another process starts running in the CPU. Now the hardware is using the other process's page table in physical memory, okay? So how can the hardware start using that other page table? Basically, we have 2 registers for that. Page table base register, which is pointing to the current page table of the current running process. All right? So whenever you context switch, you load that register with the address of the page table of the new process that is to be run. Okay? So that register basically, PTBR register basically points to the current page table of the current running process. Points to the page table of the current running process. When you change the current process to another process, then you change that pointer to point to the page table of the other process. Okay? So, and also we include a length register here indicating the size of the page table. Now, if you have this, now while the hardware is using those page tables, what's happening? The hardware is going to the page table to obtain the frame number and builds a physical address, and then it's going to that physical address in memory. So to go to the page table to obtain the frame number, the hardware makes a memory address, access, because that page table is in memory. So to go to the page table and get the frame number, we make a memory access. And then we obtain the physical address and we go to that location to get the value, we make another memory access, okay? So this may slow down actually the process, because now every memory access or reference requires 2 physical memory accesses. One for the page table and one for the value to get from into CPU. The value may be just a variable value or it can be an instruction actually, okay? So how can you speed up the process? We will talk about that, but before that, let's look to the implementation of the page table again. So in the main memory, in the RAM, we have kernel memory and memory allocated to processes in terms of pages, okay? So the kernel memory will hold the page table of the processes. Each process has its own page table, right? Remember, each process has a PCB, right? Process control block, a structure to keep information about that process. That structure may have a pointer, for example, to the page table of that process. So each PCB has a pointer to its page table, okay? So when, for example, the CPU is running a program, let's say program 1 here, right? The PC counter of the CPU, instruction pointer of the CPU will point to some instruction of program 1, right? It is the current instruction or next instruction to be executed, okay? And we said that we have also a pointer, a register called PTBR, page table base register, that's pointing to the page table of the currently running process. So if the currently running process is P1, that means that PTBR register will point to the page table of that process, right? It will just include the address of that process. It will include the page table address of that process. So if a context switch happens now, if we switch to another process P2 and start running that in the CPU, before doing that, as part of the context switch, we have to do what? We have to change the PC value to point to here. That PC value will be obtained from the PCB2, and we also change that pointer to point to here now, okay? To the page table of the second process. So the context switch will include the loading of that register as well. So that you change that pointer now to point to the page table of the second process that will be running in the CPU now, okay? So this is what's happening while we context switch the CPU between processes. You have to change the page table that the hardware is using. After that time, while the second process is executing, now the hardware will start using that page table to do the translation for that process, okay? Previously, it was using that page table to do the address translation for the previous process, okay? So now, as I said, for example, if program 1 is running, okay, if program 1 is running in the CPU and it would like to make a memory reference, it generates an address. That means it would like to get a value from that memory address. So it's a logical address that has to be converted to a physical address. For that, you consult to the page table. The hardware consults to the page table which is sitting in memory. So that for that, we make a memory access. Right? A logical address is generated by the CPU. To find the physical address, we need the frame number containing the page number. So for that, we go to the page table in memory, and this means we make a physical memory access to retrieve the frame number. So this is one memory access. And then after retrieving the frame number, we obtain the physical address by concatenating the frame number with the offset. So then we go to that location in the memory and retrieve the value from that. So this is a second memory access, physical memory access. That means if you always go to the page table to do the address mapping, that means for every memory reference done by the executing program in CPU, you need to make two physical memory accesses. This is slowing down your computer, okay? So how can we speed up? So that we don't have to go to the page table for every translation. What can we do? We can apply the caching idea, right? We can cache the translations, all right? So that is actually a cache called translation leukocyte buffer that can be sitting as somewhere in the CPU, okay? So we can solve this problem by using a special fast lookup hardware cache called associative memory or translation leukocyte buffer, okay, TLB. So then what do we store in the TLB? So after we learn, for example, the corresponding frame number to a page number, we store that association mapping, frame number, page number, frame number mapping in one entry of the TLB, okay? And this is useful because when you learn that mapping, when you reference that page number, you will probably reference the same page number again, because a page is 4 kilobytes that can contain many instructions or many variables. So after you access one instruction from that page, the next instruction will also be in that page, the next instruction will also be in that page. That means the addresses of those instructions will have the same page number. So you can satisfy the translation need from that TLB entry. You can immediately find the frame number, corresponding frame number from the TLB for that page number, okay? Because you have already cached that. The initial translation is done by the help of the page table, then you cache it in the TLB, and the subsequent translations can be done from the TLB. Okay, this works fine. And since TLB has many entries, you can actually store other mappings, up to, for example, 64 mappings and so on. So we can also keep in the TLB the identifier of the process to which that page belongs to, because when you context switch, you will start running a new process that will have a new process ID, which may refer to a similar page, but that page is actually sitting in some other frame, so that means a different translation. So that binding or that translation should be a separate entity in the TLB. In order to not mix up the page number, frame number mappings among different processes, you also associate with each mapping the process ID to which that page belongs to. Okay, so we call that as the address space identifier. That's this basically the process ID of the process. Some TLB store also the process IDs. So what is the benefit of that? The benefit is this. Assume you are running a process. It is using TLB for address mapping and so on. Okay, so it has page numbers and frame numbers in the TLB. So when you context switch to a different process, if you do not have those identifiers, if you do not keep in every TLB entry the process ID, you have to flush the TLB, meaning that you have to erase it so that those entries become invalid. Because the new process will make maybe similar page reference to the same page numbers, but those page numbers need different mapping. They are not loaded into the same frames, so they cannot use the existing entries belonging to the previous process. Okay, so they have to be flashed. Therefore, if you don't want to flash, then you have to associate the process ID to each TLB entry. Okay. Any questions so far? So now the TLB can simply look like this. It's a sequence of entries where each entry has two fields, page number and corresponding frame number. You learn that mapping by first going to the page table. And then when you learn that, you install it here, you put that here, and the remaining translation needs can be satisfied from here. If you want to convert a page number to a frame number, you first search that table, whether you can find a matching page number. If you can find a matching page number, then you can immediately obtain the frame number. Okay? So then, what is the hardware? What hardware will look like with TLB? So CPU will generate logical addresses that can be considered to be divided into two parts, P and D. P is the page number, D and displacement, D displacement or offset. So you need to convert that page number to a frame number in order to find out the physical address corresponding to that logical address. So how do we do that? Normally we go to the page table to do that translation. But now with TLB existing in the CPU also, you first go to the TLB, search the page number here. If it is there, you obtain the frame number directly. And then use it here, concatenate it with D, and obtain the physical address. Access to TLB is much faster compared to accessing a page table sitting in memory. TLB can sit, for example, in the CPU itself. Okay? So that means if the page number is here, access time to TLB is very small, epsilon. Okay? But if it is not there, if the page number is not there, for example, this may be the first reference to that page, then you have to go to the memory. If you could not find it here, again, you make a TLB access, right? You search the page, you cannot find it, and then you go to the page table in physical memory, use that page number as an index there, and then you obtain the frame number from the page table. You use that frame number, concatenate that with the displacement, obtain the physical address in this way, and then you go to the physical memory again. So if you follow that path, you do how many memory references totally? Memory accesses? Sorry? 2, right? 1 to access the page table, and then to access the value sitting at that physical address. Is it clear? However, if you can find the page number here in the TLB, how many memory accesses, physical memory access do you need to the RAM? 1, right? So then, depending on the ratio of times when you can find the entry here or there, your speed will be different, right? So you can compute the effective memory access time depending on the hit ratio. So what is the effective memory access time? How can we compute that depending on the hit ratio? The hit ratio is the percent of time that you can find the page number in the TLB. Okay, 1 minus hit ratio will be the percent of time that you cannot find it in TLB. So hit ratio will be a number between 0 and 1, a real number, okay? So assume that it takes epsilon time unit to access the TLB, okay? Access the TLB and performing a lookup there takes epsilon time unit, okay? Now we will compute the effective memory access time. So assume this. And assume now memory cycle time, memory access time is 1 microsecond. You go to the memory and retrieve a value from there. It takes 1 microsecond, all right? And epsilon is much smaller than 1 microsecond, assume, okay? So now hit ratio, assume, is the percent of time that a page number is found in the TLB, okay? Of course, this hit ratio is related to the amount of the TLB entries that you can have. The more TLB entries you have, the bigger will be the hit ratio. It will be closer to 1, okay? So hit ratio is a real number between 0 and 1. So it is percent of time that you can find the entry in TLB. And 1 minus alpha will be what? It will be the percent of time that you cannot find the entry in the TLB. So then the effective access time to memory is what? It can be computed like that. So alpha percent of time, you can find the entry in the TLB. That means during this time, the memory access time will be what? You will just access the memory once, 1 microsecond, plus you are going to the TLB, epsilon microseconds, or epsilon time units, which is much smaller than 1, okay? So the total access time will be 1 plus epsilon. How often you observe that access time? Alpha percent of time, okay? So alpha percent of time, your memory access time will be 1 plus epsilon. And 1 minus alpha percent of time, that means you are not finding the entry in the TLB. You go to the memory for the page table access and then value access, 2 memory accesses, plus you also search the TLB so that you cannot find the entry. So epsilon time unit comes also from there. So the total access time will be now 1 plus epsilon, 2 plus epsilon, okay? So you spend 2 plus epsilon time to retrieve a value corresponding to a logical address from the memory, okay? In this second case, where you cannot find the entry in the TLB. And this happens 1 minus alpha percent of time. So these are the weights. Alpha and 1 minus alpha are the weights. So then, this is you can just do the algebra here and obtain this value as the effective memory access time. What is that? The effective memory access time here in this particular example, it is 2 plus epsilon minus alpha microseconds. Epsilon is a very small number compared to 1 microseconds, okay? So if you ignore that, so the effective access time will be 2 minus alpha, where alpha is the hit ratio. So the bigger the hit ratio, the smaller the effective access time. So what is the maximum value of the effective access time in this case? Alpha will be 0, hit ratio is 0, then effective access time will be around 2. If alpha is 1, hit ratio is 1, that means you can always find the page number in the TLB, then the effective access time will be close to what? 1, right? Okay, so this is how you can compute the effective access time. So basically you will try to increase the hit ratio by maybe using more entries in the TLB and so on, okay? Any questions? So memory protection with paging scheme can be implemented by associating protection bits with each frame, okay? Then access to the frame can be protected. Additionally, in the page table, you can keep a valid invalid bit attached to each entry in the page table. So that valid bit will indicate that the corresponding page is actually used by the program at the moment. If that bit is invalid, that means the corresponding page is not used by the process at the moment. That means it is not in the logical address space of the process at the moment. So what does it mean? It means this. Assume we have a program. This is the logical address space, logical memory of the program, okay? So these are the pages that are used at the moment by the program. Logical pages, okay? They store the content. Maybe some instructions, data variables, and so on, okay? So the potential logical address space, the largest logical address space that the program can use, assume it is larger than that, it is 8 pages. Assume the largest address space that a program can have is 8 pages. All right, but here it is just using 6 pages because the program is enough to occupy the 6 pages. Okay, it doesn't need all 8 pages. 2 pages are unused. This can happen, right? You can have, for example, a logical address space that is 4 GB, but you can only use some portion of that. Your program may be a small program. Not all programs are equal size, and not all programs fill all the possible logical address space. So in, for example, Intel machines, 32-bit machines, the logical address space can be 2 to the power 32 bytes, which is 4 GB. This is the size of the logical address space, but your program is not filling all the portions of that logical address space. Some number of pages are used, okay? Out of maybe 1 million possible pages that can be in your logical address space, only a few number of them may be used, okay? So then the corresponding page table will have actually an entry for all possible pages that a program have. So here we will have 8 entries, okay? But some of those entries will be unused because they correspond to the pages that are not used by the program at the moment, okay? So for example, here only these pages are used, pages 0 through 5. So therefore, we have the corresponding frame numbers here written in the page table. So for example, page 3 is loaded into frame 7. So we have that information here. And we also have the valid, invalid bit set to valid here, indicating that that page 3, is used by the program. It is used by the program, okay? And however, page 6, it doesn't have a corresponding valid frame number, and the valid invalid bit is set to invalid, indicating that the program is not using that page 6 at the moment, okay? It's unused. So if your program is actually making a memory reference to an address here, that's an illegal memory reference, okay? So if you are, for example, trying to access a pointer value, data pointed by a pointer variable, and if you did not allocate memory yet, what happens in your program? You get a segmentation fault error and so on, right? So you may try to access a region of your logical memory that is not allocated yet, or that is not defined to be used by your program. So if you try to do that, then the hardware will catch that, because it will try to do a translation from that page 6 to a frame number, but it will see invalid bit here, and it will trap, okay? It will stop running the program, and it will trap into the operating system. So OS will write a message to the screen, invalid memory access, and so on, okay? So therefore, this shows that not all portion of your logical address space is used by the program. Only a tiny portion may be used. The remaining pages may be unused. Then you have to mark the corresponding entries in the page table as invalid, okay? And paging architecture also helps us to have shared pages, shared code. So a program, for example, that is loaded into memory may have some private data, some private code segment that's only executed by that program, used by that program, and that is the data will be operated only by that program, okay? Plus, sometimes you may define a shared memory area, so you may have some shared data. Also, you may have some shared libraries. Some segment of the code may be shared by different processes. So it's possible that different processes may execute the same code. All right? This may be a need. So with paging, you can implement it very easily. So you can have shared code. So we show here an example. Assume now we have a program, let's say text editor program, okay? ED program, editor program. So assume we actually run that program 3 times. That means 3 processes are created running the same program, okay? So do you need that? You have to have 3 code segments, allocated space in memory for these 3 processes, or 1 segment would be enough, because each of these processes will run the same code, right? Assuming the code is reentrant code, can be run by many threads and processed at the same time, then it's enough to have a single copy of the program code segment in the memory, and all the processes can use that. So then, assume we have three processes, P1, P2, P3. The logical address space of each process will look like this. Some portion of the logical address space, the first 3 pages, for example, will include the code of the program, text section, okay, instructions. And the remaining page may occupy the data of the program. For example, when you use an editor, you type some characters. Those characters are stored in a variable inside the text editor, right? In a buffer. So that buffer will be sitting here. Since each process may have actually a different user attached to it, so each user may type different things, so the data part should be definitely different, right? But the instructions that are executed will be the same for each process. Then what can happen? So each process will have the same instruction pages mapped into their address space, but each will have its own data, okay? So when actually those programs are sitting in the physical memory, the frames, when the frames are allocated to those processes, you need to allocate 3 frames to hold the instruction pages. So those frames, okay, allocated, and that's enough. All these 3 processes can share those pages, ED1, ED2, and ED3, so that their page tables will just point to that 3 frames. So the page table of that is pointing to frame 3, 4, and 6. Okay, 3, 4, and 6. The page table of that, the first 3 pages are pointing again to the same frames. Here again, the first 3 pages are pointing to the same frames. In this way, these processes are sharing these 3 pages, okay, that include the instructions of the program. But now each process has its own data. So for the data for this page is sitting on a different frame, and that page is sitting on a different frame, and that page is sitting on a different frame. So that the data sections of the programs are allocated distinct physical memory areas. Okay, so that, for example, the process user here may type something, and that will be stored here. Another process user may type something, and that will be stored here, and so on. The users don't have to type the same thing, right? So they will have different data sections and physical memory allocated to the data sections differently. But here, the physical memory allocated to the text section is the same. And all these processes are using the same text section, the same instructions, all right? Therefore, we allocate just 3 frames, and it is shared. Those pages are shared by all these 3 processes. Is it clear? So code sharing is feasible in this manner with the paging architecture. So then we will talk about the structure of the page table, how we can structure the page table and so on after the break, okay?